Okay, so here what I want to do is I want to keep going with chapter P, section 5, which again is rational expressions. We have been doing that already. And not only that, just see something. Okay, and also again, not only that, we've been dealing with rational expressions. Excuse me, I lost my train of thought. So we're looking at them and what they are. And we saw last time that they're just polynomials. They're just basically fractions of polynomials, so to say. That's really all they are. It's kind of like with what do you call it, the integers, if you remember. And then you can make rational numbers, right? You basically take fractions of integers. Well, here we're doing rational expressions, which are fractions of polynomials. Okay, that's good. So now what we're going to do is we're going to keep going with this. Last time we saw what it meant to multiply and divide rational expressions, and it's really just like with fractions of integers. Same process, actually. For dividing, you have to take the reciprocal of the second expression, and then you just multiply like you normally would. You multiply numerators together, and you also multiply denominators together. That's all it boils down to. Okay? And not only that, we also looked at simplifying rational expressions. Basically there, you want to eliminate any common factors in the numerator and denominator. So we'll see some more examples of that today, and we'll look at adding and subtracting. When we add and subtract, remember, you have to get just like with fractions of integers, right? You need a common denominator, and that's what we need as well, as we'll see. So here's this example with dividing, right? As you can see. Okay. So how do we divide? Remember, what we want to do is we have to take the reciprocal of the second expression, the second fraction, that is. Okay? Namely, we have to flip it, and then we just multiply, as we're doing here. That's what I'm doing from here to here, okay? We flip it, right? We take the reciprocal, we get this. Now we multiply, and now when we multiply, we're going to get this. Now you might be wondering, wait a minute, why didn't he actually multiply the polynomials together? In other words, why didn't we FOIL, right? Well, we want to simplify. And when you simplify, you want to factor, right? I don't think it would make much sense to multiply and then just factor again. And then just, factor after that. Since it's partially factored already, this saves us a little bit of work. Okay, so we have to factor. Well, the numerator here, the x plus 2 and x minus 9, you can't break those down any further. So what we're going to do then is this. We can factor this, as you can see. Okay? And not only that, and so how do we factor this? Excuse me. Well, we need two numbers, right? Notice the form this is in. It's a trinomial. It's degree 2, right? So it's essential, and the leading coefficient's 1. So we need two numbers whose product is the constant term and whose sum is the coefficient of x. So we want two numbers. I mean, I know they're here, but we want two numbers whose product is minus 18 and whose sum is minus 7. And as you can see here, minus 9 and 2, okay? Those are the numbers we're looking for. So we get x minus 9 and x plus 2. So we get this. Here, we know that 4 is a perfect square. We have a difference of two perfect squares. 4 is 2 squared. So we get x minus 2 times x plus 2. So when we plug those back in, right, as you can see, we factored. Now there's some factors we can cancel. For instance, let me use the pen now. For instance, we have x minus 9. Those are canceled. We have x plus 2. Those are canceled. And it looks like that's it. Right? You can't cancel x plus 2 and x minus 2. I know it's tempting to do that, but you can't do that. You can't cancel them, that is. But this is what we get. Notice I also said leave the numerator and denominator in factored form. And that's what we're doing here. I mean, here there's not much more you can do with this anyway. So, but if we had, let's say, I don't know, x plus 2, but if we had another factor in the numerator or denominator, we don't have to multiply them out. We could just leave it in factored form. All right. Are there any questions about this? Okay. So that was one example. Now remember, we also simplified, right? I figured it would be good to do another simplification example. So that's what I have here. Basically, to simplify, you have to factor. Okay, the numerator, we can see right away there's a factor of x. Let's dive right in and try and deal with that. I mean, the denominator we can factor. We would have to use the AC method. I mean, that's not terrible, but let's try the numerator first. Excuse me. Sorry, there was something on my glasses. I got it off. So we have x cubed plus x squared minus 2 times x, okay? So notice right away, you can see there's a factor of x, right? And we can factor, and in other words, every term here has an x in it. So we factor out the smallest power of x, which is just x itself, x to the 1. But then, we divide to see what's left over, as you can see. Doing that, we get this. Okay. And now when we actually divide, x cubed over x, right? Remember what you do, you subtract the exponents. So we have x squared over here. We have x squared over x. 2x over x, like so. Okay. So that's our numerator, as you can see. Now, this is a polynomial that's very similar to, well, it looks like this one, right? This one, remember, you have 3 terms, degree 2, leading coefficient's 1. So let's try factoring this. Since the leading coefficient's 1, it doesn't look terrible. We need 2 numbers whose product is the constant term and whose coefficient, and whose sum is the coefficient of x, which is 1. Remember, if the coefficient's 1, we do not write it. I know we have the numbers here. It looks like it's 2 and negative 1. Their product is negative 2. Their sum is 1. So those are the numbers. So we have x plus 2 times x minus 1. And we get this. So we have the numerator is this wonderful thing, as you can see. But notice we're not done with the problem though, right? We have to handle the denominator. Now this is a trinomial. This is a trinomial. The leading coefficient, it's degree 2, and the leading coefficient is not 1. I thought that was a mistake, but that's not. Well, I guess in spelling there is. I don't know if that's a word, but we can see though that we don't know if it's simplified or not. We have to somehow factor the denominator. I mean, we could do that using the AC method. But last time we also saw that we could factor this, right? We could see if it's simplified by using the factor theorem. So let's see if that helps us here. Well, for this to not be simplified, the denominator would have to have x plus 2, or x minus 1 as a factor. Right? For it to not be simplified, there has to be a factor, a common factor, among numerator and denominator. Now for this, though, as I basically rewrote the factor theorem here, for this special polynomial, though, this will have a factor of x minus a exactly if this polynomial, right, maps a to 0. In other words, if a is a solution of this equation. So all I'm doing here is I'm stating the factor theorem for this polynomial.